Don't laugh. It just works. It gets worse every year. Okay, so here's what we're going to do today. We're going to go over a bunch of fairly basic things that I'm pretty sure all of you have heard about. These are basics of probability, but we're kind of going to redo them using some of the linear algebra that we know, and we're going to describe them sort of in a way that's going to allow us to go forward in the course and use them in ways that you haven't used before. At least that's the hope. Okay, so in order to get there, here's where we were last time. And I'm going to, we were talking about data in 2 dimensions. So we'll just go through everything today. I think we'll talk about is 1 or 2 dimensions, but it generalizes. Again, that's one of the main points of using all of these tools, is that they give us, the 2-dimensional case is going to give us ideas about how we can use things like linear algebra to generalize all of our ideas and use them on data sets that are in high dimensions. So that's kind of where we're going to end up. We won't do that today, but you'll see the beginning. Okay. So everything I want to show you, I wanted to go back to this and kind of go over a few things about this, because some of these are reminders and some of them are kind of, again, pointing forward. So first, imagine I'm going to clean up something that Mike complains that I don't do correctly every single year, so I'm going to try to fix it now. First, I have data that are xy coordinate points. Okay? So I'm going to imagine that the data are in a matrix, and I hope I have all of this consistent in my examples. I'm going to assume that the data look like this. So the x's, I'll make a vector x that has all the x coordinates. That'll go along one row. And then I'll make a vector y that has all the y coordinates. It goes along the next row. And I'll put those all together in a 2 by n matrix. Okay, so this thing is n data points. And in this direction, it's 2. Okay. We've seen things like this before. You've done things like this in the homework. Okay, so these are just, every column here is a data point. The xy coordinates of a data point. There's the data points are scattered around. Okay. So the first thing we want to do, when we have a data set like that, is we want to calculate the mean. The mean is easy to write in linear algebra. It goes like this. We take d, we're going to multiply it by a vector of 1s. Okay, so this is a vector, a length n vector of 1s. It's a column vector. When we multiply that by that column vector, what it does is it sums up each of the rows, right? This matrix times a column vector. So it's these rows dot product with that vector of 1s. The vector of 1s just adds up all the elements. So we're adding up all the x's, we're adding up all the y's, and we're missing one thing. We have to divide by n if we want it to actually be the average. We add them up and divide by n. Okay? So this thing gives us a vector, a two-dimensional column vector. We can call it mu, which is the mean. And it's a 2-dimensional vector because it has in its components the mean of the x's and the mean of the y's. Right? It's a vector. And we might call that the centroid. I think I put a red dot on the slide. Yeah, there's the centroid. And it looks like that. And this, all I just wrote is the same as what's written on the slide. This is written out in terms of summations. And that's just written as a matrix multiply. But you guys have now seen this notation enough to sort of be able to interpret what this is and to recognize that it's the same as that. And we don't have to write that summation sign. We can just do a matrix multiply. And the summation is included in the definition of matrix multiplication. Okay, so that's good. Now what we want to do is we want to subtract off the mean from all the data. How do we do that? So if we subtract off the mean, what we need to do is take d. We have to subtract off of the x coordinate. We have to subtract. And by the way, maybe should I prove this? No. Well, yeah, let's start. We'll do that. So simple property of the mean. It's sort of an obvious property. This is a linear operation on the data. It's a weighted sum of the data. So because it's a weighted sum of the data, it is a linear operation, and that means that if I do something to the data, like if I transform it, then the mean of the transformed data will be the same as if I transform the mean. Okay, so I said this last time, but I wanted to make sure that everybody understands what we're talking about. Okay, so how does that work? Well, imagine I want to project onto some vector v. So my data are over here, and I have some vector v, and v is going to, or w, let's say even. I want a weighted sum of the x and y coordinates. This doesn't even have to be a unit vector, it can be anything. So how do I do that? Well, it's just written like this. So w is a column vector, a two-dimensional column vector. If I do this, w transpose times d, what does that compute? W is a two vector. I'm transposing it, and then I'm multiplying it by d. And what I'm doing is I'm just taking the dot product of w against each of these x, y pairs, right? I'm just taking the weighted sum. And we know that that basically corresponds to taking all of these data and effectively projecting them onto this line, right? And now you can ask yourself, okay, if I do that, so now I have the data line on this line, you know, this point goes here, this point goes here, this point goes here, I have the data points lying along this line, here they are. If I drew a histogram or a distribution, maybe like that. What's the mean of that thing? The mean of the values along this line? Well, I can go through and calculate what is the mean of this, right? How do I do that? I just take all of these guys and add them up and divide by n. But since this thing is linear, I can write mu w. This is the mean after I take the product with w. It's just going to be a scalar because these values are scalars. And that's equal to, well, it's like taking, the way I take means of things is add them up. So if I wanted to, here, let's just define it. It's this. So that thing is a row vector, a great big row vector with n samples, because it's the result of taking each data point and smashing it onto w. So I get n of those. This is a row vector. And how do I take the mean of the row vector? Well, the same way I took the mean of the two-dimensional thing, I just multiply it by this one vector, right? This is a dot product, so this is a row vector, this is a column vector that each have length n, and this just adds them up, and of course I have to divide by n. But of course, the associative rule here kicks in. This is a vector times a matrix times another vector, and if I just rearrange the parentheses, what I see is it looks like this. This is right? All I did is move the parentheses over, so the d is now first multiplied by the 1, and then multiplied by the w transpose. And what's that? Well, d times 1 divided by n was just the original vector mu. So this is just this. Okay? I'm just connecting some dots here. So what does all of that tell us? It means that if I have the two-dimensional mean of the data cloud, sorry, this is blue, and on the slide it's red. Just to be a little bit consistent. Right, so the data cloud has a centroid. It's a two-dimensional vector, which is in the middle of all the data. If I smash the data onto a line, the centroid, or the mean of the data after it's smashed onto the line, is just the mean out here smashed onto the line. And that means, of course, as I think I described last time, I wanted to make this clear, if you calculate the mean on a high-dimensional data set, and you think of that as a way of summarizing the data, you can now calculate what that will look like if you do various transformations on the data. In particular, if you multiply the data by actually any linear operator. Here we did a dot product with a vector. But if this was a matrix, the same thing would hold. Everything I just wrote would still go through. Any linear operation, if I ask what happens to the mean of the data, if I run the data through some linear transform, the answer is it's just the same linear transform applied to the mean vector. So I don't have to go back and apply this to every data point. I can just apply it to the mean vector, And that tells me the answer. So the mean, this mean vector is a nice way of summarizing the data because I can actually count, not only does it tell me where the center of the data are, but it tells me what happens if I were to change the data coordinate system. If I were to rotate it, or stretch it, or translate it. Okay? So if I add something to the data, if I add 5 to the horizontal coordinates, that's just moving the origin, translating it. Then the mean obviously will move along with it. So that's not a linear transform. Adding a constant is not what we call the linear transform when we define linearity. But it also obeys this simple property that if I move the data, then the mean translates along with it. Right? All right. Some of these things are kind of obvious, they're intuitively obvious, but I want to make sure that you see that actually the math goes along with this, everything works. Okay, so that's the mean. Now, normally what we would do is we do exactly what I just said. We recenter the coordinate system around the mean of the data by taking all the data and subtracting off the mean vector from each of these columns. How do we write that with linear algebra? So let's do that. So we're going to define, let's call it, I guess we'll call it d tilde. Okay, so this is going to be the data recentered. Okay, and what does that look like? Well, it's just d, and we're going to subtract off. How do we make a matrix that has the mean vector, this mu, in every column? Every column has to have the same vector. I want to make that matrix, and I want to write some linear algebra that generates that matrix. How do I do that? Any idea? No ideas? I mean, I want something that has mu in it, and mu in it, and mu in it, and mu in it, and n copies of mu. These are the columns. How would I do that? How would you do that in MATLAB? You could write a loop, make a matrix, and just paste in the mean in every column for I equals 1 to n, paste, 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 paste. That's kind of what I just did on the board. But how would you do it with matrix operations? Nobody?
Use the identity.
Can you use the identity? Maybe. It's a second suggestion. What's that?
Dot product with ones.
Dot product with ones. Okay, there we go. That's a dot product with ones. So if I take a dot product of mu with ones, then that just adds up the mean of the x's and the mean of the y's, and I get back a scalar, right? So I didn't want a scalar, I want a matrix. What could I do that looks kind of like a dot product, but it actually doesn't give me a scalar, it gives me a matrix?
The
Outer product. Okay, so how are we going to use an outer product to generate that thing that we want?
Start off by what's the size of the thing you have to be multiplied, just using the multiply size rules. We have a 2 by 1, we want a 2 by n. So therefore you have to multiply by a.
So if I had mu x and mu y, that's what I want the columns to look like. And I want the way you think of an outer product is you just fill in the table, which is the matrix, by taking products of all elements of this vector with all elements of this vector. I want this vector to be like n. And so if I put the vector of ones in here, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and there are n of them, what's the outer product look like? It's going to go here. I'm going to fill in a box of numbers. They're going to go here. The outer product of this and this is going to be mu x, mu y, mu x, mu y. Right, so it's just matrix multiplied. It's completely consistent with everything we've ever done with matrix multiplication, right? But it's kind of a weird thing because I'm taking dot products of the rows of this, which are just scalars, and the columns of this, which are just scalars. Not only that, all the columns of this are just ones. So really all I'm doing, I'm taking ux times 1 and putting it here. I'm taking uy times 1 and putting it here. Then I'm taking ux times the next 1 and putting it here. Ux times the next one and putting uy times the next one and putting it here. So this is ux, uy, ux, uy, ux, uy, etc. And that fills this matrix with copies of the mean vector all the way across, okay? So instead of writing all of that out, we just write compactly linear algebra, which is that we need mu, which is a column vector of height 2. And we need 1, the 1 vector, but the 1 vector was a column vector of height n, so we're going to have to actually a little twist. We have to transpose it, right? We want a row vector of 1s. Now this is an outer product. It's not an outer product of two things of the same size. These things have different size. That's okay. Because they are suitable for matrix multiplication. You can't take an inner product of these two things, because this has length 2 and that has length n. It doesn't work. But you can take an outer product. Okay, so that fills our box of numbers, and if I take d and subtract this, I've just subtracted the mean off of every single data point.
That trick about taking a vector and copying it a bunch of times by multiplying by 1s is the right way to do it in MATLAB. It's the fast way.
Yeah, this is very fast in MATLAB. Just take these two vectors and multiply them just like that, and boom, we've got the matrix. Okay, we subtract that off of d, sorry, data. So, and all we've done in this picture is we've just transformed into a new coordinate system where the data, I guess I can draw it down here. Here's the data, here are the data, it's plural, and the mean is now sitting at the origin. All we did is we subtracted that off of every data point, so we just moved the coordinate system so that it's centered at that position. Okay, so that's the mean. Now, all we do, is it on the slide? I don't remember what I wrote on the slide. Okay. So here it's written this way, which is equivalent. We're going to define the covariance as just measuring. It's essentially averaging the outer product of all these points against themselves. And these points are in here, so we're going to define the covariance, C, which is going to be a 2x2 matrix, as this thing times itself, right? So this thing is going to be d tilde times d tilde transpose, right? Sure I have my transposes right. Yes, that's fine. And why is that the same as what's there? Well, what's there is written with a summation, but if you think about it, this is this matrix times itself transposed. And what's going to go into each entry is going to be these x's minus their mean component. I guess we can write it out. It's going to be, we can actually write it out in vector form as opposed to what's on the slide. Or actually, no, it is written that way on the slide. Let's just write it out here though. Okay, so we're going to have, there's a vector x here, and it's going to be that vector minus the mean component, the x coordinate of the mean, and then it's going to be that thing. And I have to now take the sum of squares of that, the sum of the squared values of that thing, right? So I'll write this so that it'll be easy for you to follow. Doing a bad job of explaining what it is. Do we write it all out? And then show that it looks like that? Yeah, I guess we could do that. Let's do that. Okay. We can write it out with the linear algebra, and then we'll go back and look at what shows up in the matrix. Okay, so it's this thing times its own transpose. which is, because of our definition, d minus mu 1 transpose times d minus mu 1 transpose, transposed, right? Just plugging in what d tilde is. And how do I compute that? I'm going to come up here. So I'm going to need a little more space. D times d transpose. That's just the first two terms. Then I have d times this thing transposed, and there's a minus sign there, so it's going to be d times transpose this. This is mu times 1 transposed. If I transpose it, I transpose each of those elements and flip their order. So I have to write 1, and I have to write, by the way, nobody caught me, but I left out the divide by n, as usual. And this has to divide by n. Right? You take the average, divide by n. Okay, so now, d times d transpose minus d times 1 times mu transpose. Then there's going to be a minus, well, it'll be the same thing, but we'll write it out. Minus, this will be mu times 1 transpose times d transpose. And then the one last thing, which is plus mu times 1 transpose times 1 times mu transpose. And I've run out of board space because I've done something stupid here. Tell you what, well, before we write the last term, we're going to notice that these two things are transposes of each other. Actually, let's notice something else. This thing, what is it? It's d times 1 times mu transpose. What's mu transpose? Well, here was mu, right? So mu transpose is just this transpose. So let's write that transpose. It's 1 transpose times d divided by n.
D transpose.
D transpose, thank you. Okay. So two things about that. First of all, it's symmetric. Right? It looks like this thing times itself transposed. So it's symmetric. And that means that this one, when I write this one out, it's going to be the same thing transposed, which is these two things are the same. These two terms are going to be the same. So I'm going to erase this one, and I'm going to just put a 2 here. Okay. Now the other thing we can notice is what's 1 times 1 transpose? 1 is this column of 1s, there are n of them. If I take a dot product, this is a dot product, 1 times 1 transpose. No, it's not.
No, it's not. It's not.
Okay, so we can't quite do what I was about to say. That's too bad. That's okay. All right, so this thing, I'll just, this thing's just going to sit there like that. In fact, the easier way to write it, now that I notice it more carefully, is to notice that actually d times 1, this part, is of course just mu. It's actually n times mu, right? So I'm going to replace this whole term, the cross terms, the ones that are d and the mu and 1. I'm going to replace those with, we'll do that in the next line. Let's do this first, okay? So this thing, what's the last term? Mu 1 transpose times mu 1 transpose transposed. So that's mu 1 transpose 1 and mu transpose. Okay. And this thing, and there's a divide by n, of course. So I have a d, let's rewrite it, d transpose. This thing, I'm going to replace this d1 with a mu. It's actually n times mu. So minus 2n times mu transpose. But over here, what do I have? I have mu 1 transpose times 1 and mu transpose. What's 1 transpose times 1? Now I've got it in the right order. 1 is a column vector. So 1 transpose is a row vector of 1s times itself, which is a column vector of 1s. That's a dot product. Okay, so what happens if I take the dot product of the 1 vector with itself? Well, that's the squared length of the 1 vector, right? Remember that. Dot product of the vector with itself is the squared length. But what is it? This is not any old vector. This is the sum. It's all 1s. So if I take the dot product of this thing with itself, I get 1 times 1, plus 1 times 1, plus 1 times 1. A whole bunch of those. I have to add them all up. There are n of them. So when I take the dot product of the 1 vector with itself, I get n. So this thing, 1 dotted with itself, is just n. So I have here, this just drops out as a scale factor, n, and I have mu times mu transpose. And oh look, this is mu times mu transpose. So here, I'm going to get n times mu transpose.
Whole thing over n.
Pardon me?
The whole thing.
The whole thing over n, thank you. Yes. There's still a divide by n lurking underneath the entire thing, all the way back from the beginning, right? Divide by n, divide by n, divide by n, divide by n. I'm just working through what are the numerator terms. So now we've got d times d transpose. What is that? That's like the original data, outer producted with itself. Okay? We'll say in a minute what that matrix is called. And then we've got minus, okay, there's 2 times n mu times outer product with itself. And then there's plus another n of mu times outer product with itself. And altogether, these two terms are the same, except this one is minus 2 of them, and this is plus 1 of them. So in the end, what I have is dt transpose over n. And now I'm going to move the n so it just divides the first term. And minus 2 of them plus 1 of them means there's minus 1 of them, or minus n of them, right? Because minus 2n plus n. There's minus n of them, but I'm dividing by n, so it's just minus this thing. Mu times mu transpose. So it's this thing minus this thing, and what are these? So what did we get here? We're going to find this as the covariance matrix, the sample covariance matrix. It is a 2x2 matrix, and it can be written as a difference of 2 2x2 matrices. One of them is to take the raw data and multiply it by itself. These are outer products of each raw data vector with itself, added up, averaged, because I add them up and then divide by n, averaged. Okay, so that's a matrix. And this thing is, let me give you the equivalent in 1D. If we were in 1D and we wanted to compute, we had just x minus mu. Mu is the mean. We take x, we subtract its mean, and we square it and add it up. These are x of n's, right? What would we get? Well, that's the sum of the, if we expand the square, we would get the sum of the xn squares. We would get minus a sum of xn's times mu's, and we would get 2 of those. And then we would get plus a sum of mu squares. Right? These are just scalars. I want to show you that the vector thing we just worked through is really the same as the scalar case. So what does the scalar case do? We write that, we expand the square, then we say this is equal to the sum of the xn squares. And now what? I left out the 1 over n as usual. So 1 over capital N, so 1 over capital N, out in front of the whole thing. Now I get what? This thing divided by n. Now what happens? This is 2 times the sum of the xn's. The sum of the xn's is just the mean. Well, the mean multiplied by n. So this is minus 2 times n times the mean squared. And then I have plus, this is the sum of the mu squares. I added up n times, so this is n times the mean squared. So I have 2 times the mean squared, minus 2 times the mean squared, plus minus 2n times the mean squared, plus n times the mean squared, which is again minus n times the mean squared. I divide by n, it's just minus the mean squared. So it's exactly the same calculation that we wrote out, except instead of writing outer products and vectors, this is just scalars. Okay? So in the one-dimensional case, what happens is the covariance, or the variance in this case, sigma squared we usually write, sigma squared can be written as the raw sum of the squares of the data, not centered, without the mean subtracted, this is just the raw data, minus the squared mean. Or it can be written as the way we originally wrote it, which is take the mean or the average of the sum of the data squared after you've centered it. So you have two ways to compute the variance. You can either center the data and then just take the sum of squares, or you can just take the sum of squares of the raw data, that's this, and then at the end subtract off the squared mean. Okay, what is this? We have a name for this thing. Anybody know what that's called? It's not the variance. The whole thing, the difference is the variance. So what's this thing is the squared mean. On the left side we have the variance. What's this thing that I circled? Is there a name for that? Anybody know it? Okay. So the mean is referred to as the first moment, and this thing is called the second moment. The average of the squared data is called the second moment. So what we just wrote, that thing, says variance equals, I'll just write it in terms of the math notation. We write sigma squared. Sometimes people write the second moment as m2 minus the squared mean. The mean is m1, so you could write m2 minus m1 squared. Okay? And that's a sort of general rule, and this is a sort of partitioning of quadratic forms, right? We have these quadratic elements, and we can pull it apart into these pieces. We're going to see another one of these in 10 minutes. And we're going to actually see a bunch of these as we go through the course of examples where you can partition sums of squares, variances, into pieces, separate them out. And this is the first example. This is just a statement that when you compute a variance, it's actually really, you can partition it into two pieces. There's one thing that has to do with the mean, or the square of the mean, and there's another thing that's just the second moment of the data. Okay? And you can compute this either way, they're equivalent, and the vector form of it is just this. You take your raw data and you take basically outer products of all your raw data points divided by n, and then you subtract off of that what you would get by taking the outer product of the mean with itself. It's the same expression, it's just written in terms of vectors and matrices. Okay? All right. Now, the last thing we have to do is we should just make sure we understand that this, what's written here, is exactly the same as what's written here. This is written out in terms of summations, but this matrix multiplication is computing exactly the same thing. Better be computing the same thing, because if that's the same C, the same covariance, it's got to be exactly the same as what we're writing here. And it is. Okay, so how can we convince ourselves? Can you see it? So what's going to come out of, if D looks like this, and I take D times D transpose, what am I doing? I'm taking this matrix and multiplying by itself, transposed, which means that each of these columns, or sorry, each of these rows is going to be dot producted with itself and with the other row. So I'm going to take, if I write this out, where do I write it? I'm going to erase what I wrote, the proof. So now I don't need it anymore. I have dragged you through it, and that's enough for today. I won't do that again. Okay, so C is just going to be D times D transpose divided by M minus mu times mu transpose. Okay. And D times D transpose, let's write out what that vector, that matrix looks like. D times D transpose is going to be what goes in the upper left-hand corner of that. It's this vector dot product with itself. So it's basically take the x vector, that's an n-length vector, and dot product with itself, that's just the squared length. This vector times itself, and I have to divide by n. I always have to divide by n. What goes over here? X dotted with y, or I can write x transpose y, so you all know that, divided by n. This is, if you like, we can write here y transpose x, but you all know that x transpose y is the same as y transpose x. This is a dot product of these two rows against each other, the x and the y row. So it doesn't matter which order you do it. X transpose y is equal to y transpose x. And then down here, we have the length of the y vector. So now we have an interpretation of what's going in this covariance matrix. We're not done yet, but we have an interpretation in terms of these vectors that contain, remember these vectors x and y are not the vectors that live in this space, right? These are the two components, the x and y components. These things are huge vectors, length n, that contain all the horizontal coordinates and all the vertical coordinates of your data points, right? This matrix, D, has each column is an xy coordinate for one point. But if I think of the rows, it's take all the x coordinates, take all the y coordinates, right? All right. So now I'm going to do minus. I have to do the subtraction, right? And minus, well, this thing is the outer product of mu with itself, so what does that look like? Well, it's just mu x squared goes up here. This is mu x times mu y. This is mu x times mu y. And this is mu y squared. Okay? That's just taking this little vector mu. It contains mu x and mu y. It's mu x and mu y. Right? We're taking the horizontal and vertical component of that and taking an outer product of that with itself, so I get the square of the x's here, the product of the two here. It's symmetric, so I get the same thing down here, and then this is the y. Okay. And that thing is the same as what's on the board, because this is an outer product of each data vector, so it has the horizontal coordinates squared in the upper left-hand corner and added up and divided by n. That's just this. The sum of all the horizontal coordinates squared, added up, divided by n. Sum of all the vertical coordinates squared, added up, divided by n. It's just a shorthand way to write that thing with the summation. So these are, again, things that you already know about. We're just using them to rewrite something that's a covariance. And it'll give us a little bit of interpretive power when we think about what this thing is. Okay, so let's do that. I already mentioned what happens if I transform the data. So we did a subtraction to subtract off the mean. We can also think about what happens if I transform the data using a matrix. We did one example where we used a weighted sum, W, but we can use any matrix we want. And if we do that, what happens? So if I write, I don't know, let's do a transformation of the data, which looks like A, matrix A, times D, right? So what happens to the mean? We already talked about this. So the mean of AD, if this is the new data, the mean of AD, so here, if I write D tilde equals AD, then the mean is just D tilde times 1 over n, which of course is just AD times 1 over n, which is just A times the original mean. Okay, that's the same as what I already told you with W. So if I transform my data using A, then my mean also transforms by A. What happens to the covariance? Okay, so now I write the covariance of AD is equal to what? Well, I have to do all of this. It's, well, let's write it out. Let's write it this way. Let's write the covariance of D tilde is going to be D tilde times D tilde transpose over n minus mu tilde times mu tilde transpose. Okay, so I'm just using this formula that we have for covariance. And that's equal to tilde is just AD. So this is just AD times D tilde transpose, which will be D transpose A transpose. Okay, so that's writing this out, divide by n. And then what happens to this? Well, mu tilde is just A times mu, so that's A mu. And then I have to do mu tilde transpose, so that's mu transpose A transpose, and there's no divide by n on that. And now I notice that really, I can factor the A and the A transpose out of this, because both of these terms have an A on the left and an A transpose on the right, so I can write that. A transpose times D transpose over n minus mu transpose like this, and then there's an A on the other side. And I've already gotten it backwards. This is the A transpose and this is the A, sorry. Okay, so there's an A. I've just pulled the A out of both terms, pulled that out to the left, pulled the A transpose out of both terms, pulled it out to the right. Can't change the order of multiplication because these are matrices, right? So I pull the A's to the left, the A transposes to the right. Now I have this thing in the middle, and what is that thing in the middle? That's just C. So all we're doing is convincing ourselves that if we transform our data, this is the point of all this stuff on the board, if we take our data, our XY coordinate points, and we do something to the space that they live in, I change the coordinate system, and that can include translating the coordinate system, that's just subtracting something off, or multiplying by a matrix, like a 2x2 matrix, which you know what matrices do. They can rotate the space, they can squeeze the space, and in fact, using SVD, you can describe the matrix operation as doing some combination of rotating and squeezing. But whatever it does, whatever the matrix, I didn't say anything about A. A could be any, and A is a 2x2 matrix here, but it doesn't even have to be that. It could be a 1x2 matrix. It could just be taking a weighted sum of the data, as we did with that W earlier. Okay? Whatever I do to the data, if it's linear, multiplied by a matrix, then the covariance transforms like this. Okay? So I do this to the data, and instead of going and applying A to every single data point, if I want to know, well, what happens to my summary description, I know. I just take the original summary description, which was the mu and the C, and I transform the mu using this, where is it? I've erased it, no, this rule. So here, this is, let's say, mu tilde is equal to A times mu. So the new mean is just take the old mean and multiply it by A. And what happens to the covariance? This is like C tilde. What happens to that? I just take the old covariance, C, and I don't multiply it by A. I multiply it by A on the left, and I multiply it by A transpose on the right. Okay, so there's this little trick there, right? That the way that C transforms is not the same as the way the mu is transforming. The mu is, that's the mean. This is a kind of second order quantity. It's quadratic. It has squares in it. And so when you transform it, it has to get like transformed twice, is the sort of intuition, right? I have to hit it on both sides by A, not just once. I have to hit it by A and A transpose. Okay? And that's how it transforms. The new C is the old C hit on both sides with A. Question?
Euro d tilde equals A times D. Is that the same d tilde as D minus?
No, I'm being bad with notation. I'm sorry about that.
This is just the transform data, right?
Yes. This is a new D tilde.
Oh shit.
Everything's written over there. This is bad notation. Erase. I used D tilde here just on my way to defining C. Now I'm going to erase that D tilde. I make a new D tilde. This D tilde is A times the data. Okay? Sorry about the notation.
So that's what happens when you do something linear. And Eero also said that if you add something to all your data,
Yes.
the mean just gets it added. If you add something to your data, that cloud just shifts, so the mean shifts with it. And the covariance doesn't change at all. That's the last piece to
Yeah.
you say.
Yeah, but I don't want to write it out.
No need. I mean, it's sort of obvious. If you move the
Yeah.
cloud, its shape doesn't change.
In the end, a lot of this is very intuitive and obvious. But I wanted to kind of walk through a little bit of it so you can see that actually you can make it very tight, and you could use the linear algebra notation that we've been using in order to sort of convince yourselves that these things have to be true. Okay, so we have data clouds. We know now how to calculate the mean and the covariance as a way of describing or describing the data, capturing some properties of the data. Basically, the mean captures where the central tendency, where the data lie in this full space of this, let's say, this plane. And the covariance describes not just the width of the distribution as it would in one dimension, right? The variance is just a way of measuring the dispersion. But in 2 dimensions, you have to capture the shape of the distribution. It's not just, there's not just one width. It's like how wide is it in all directions? And we know from all the stuff that we did with total least squares and thinking about quadratic forms when we went through all of that section of the course, this covariance matrix is going to capture essentially the shape of the data because it embodies the fact that the width of the data in any direction can be calculated just by taking the covariance matrix and making a certain measurement. So what is that? If I want to know how much do the data vary in an arbitrary direction, what do I have to do? So I have my data. And again, I'm going to assume it's now centered at the origin. I've already done the subtracting off the mean thing. And I want to know, well, if I were to smash the data onto some line, let's say that goes in this direction, I'm going to drop every data point down onto this line. And I want to know that, and then I have a distribution of data along that line, and I want to know, well, where's the center, where's the mean? Well, we know what the mean is. The mean is just, we can compute the new mean from the old mean. Why? Because this is a linear transformation. So to do this, I need a unit vector u. Let's call it u hat to remind ourselves it's a unit vector. That's what we've been doing all along. So here's a unit vector u. And to take the data and smash it onto this line and measure its coordinate along this line, all I have to do is take each data point and multiply it, or take a dot product with u. That's not mu, it's u. I just said mu. U. How do I take a dot product with u? Well, I have to take u, which is a column vector, and I have to multiply it by each of these columns, right? Dot products. And that's going to give me a bunch of numbers. It'll give me n of them. Okay, so how do I do that? How do I write that? I just take u hat, and I have to transpose it and multiply it by d, right? Why did I transpose it? Because I want, u hat is by, typically it's a column vector, it's a 2 vector, right? It has 2 coordinates, x and y, it's a column vector. I want to take it and dot product it with each of these columns. In order to make the linear algebra right, matrix multiplication right, I have to take its transpose. So I have a 2 vector that's lying on its side, and I'm going to take that times d, and that would basically be that row times dot product of each of these columns. Okay, so that gives me an n vector that's a row vector. Okay, so I want that thing, and I want to know what is the mean of that thing that comes out. Well, we can just use our usual rule. How do we get the mean after we transform? This is basically transforming with a matrix. It's just a special matrix that happens to be just one row. That's okay. What's the mean of this thing? I'm realizing that this is a very bad notation because the mu and the u are just going to be impossible to distinguish. So I'm just going to flip this to u, okay? Instead of u. It'll just be easier for us to keep track of, okay? I only wrote it in that one spot. So it's v hat, which is a unit vector. And the mean of this, the mean of v transpose times d is just, of course, v hat transpose times the original mean of the data. Okay, so it's basically take the original mean of the data, and I'm just using this rule, right? The new mean is the old mean multiplied by transform. The transform in this case is just multiplying by v hat. Okay, so there we go. The new mean is just d transpose times mu. If we already centered the data so that the mean is 0, then this is v transpose times 0, so it's 0. It stays 0. Okay, what about the new covariance? How does that transform? Well, there's the rule, right? Covariance of the data splattered onto this line is just the covariance of this. And that covariance is, it's the rule we just said. It's, A is now v hat, so it's going to be v hat times C, the original covariance. Let's write it out as D, times D transpose times v hat. Okay. And we can check a few things. If v hat is equal to 1, 0, it's along the horizontal axis, what is this going to do? So this is just to be clear, this is just the original covariance multiplied on both sides by v hat. Okay. That's the covariance, and I'm multiplying on both sides by v hat. It's this rule. It's just that now A is equal to v hat. All right.
What's the transpose? Is it, because there you have it on the...
I know, I wrote it, it looks funny because here it was on the right side and here it was on the left side. I did not make a mistake. Okay. So A here,
Only one shape.
I know you're used to me making mistakes, but here A was an arbitrary transform, a matrix. And I was multiplying A by the data, A times D, that was the idea. Here, here, the A that I want to use is not a 2x2 matrix. It's a row vector. Why do I want to use, and that's perfectly legitimate A. It can be any matrix that makes sense to put here to multiply by C is usable. So I need, the basic rule is that the A has to have 2 columns because I'm going to multiply it by D. And D has 2 rows, so for the matrix multiplication to make any sense at all, it has to be the case that A has 2 columns. Okay, this is a vector. It has 2 columns because it's a row vector, and it's just that one vector. So here A is equal to v hat transpose, right? And then if you go through the rest of it, this is just the same as that, right? The transpose has got split to the other side. Okay. Anything else we need to say about this? Yeah, I just was going to give 2 examples. This is more along the lines of, let's make sure we understand what this covariance matrix is. So the covariance matrix, I already wrote and erased something which said that it looks like something like this. The squared length of x divided by n. This is x dot y divided by n. This is x dot, or y dot x. Same thing. And this is the length of y, right? So I had this written on the board. I'm leaving off the subtracting the mean. I'm just writing this piece. Sometimes we use shorthand notation for these things. It's very common. You find this a lot when you read papers. But instead of writing all that kind of thing out in terms of linear algebra, people write the following notation. They kind of use the scalar notation. So they would write here, sigma x squared. I'll explain in a second why that makes sense. And then they would write something like sigma xy here. And then they would write sigma y squared here. And over here, this is the same. It's a symmetric matrix, so this is sigma xy again. Okay. So that's a 2x2 covariance matrix. I don't really like this notation so much because it kind of works nicely if you're in a 2-dimensional case, but if you go to 3 or 4 or 5, then you've got subscripts all over the place and it just becomes sort of a mess. But in any case, we can think about, so what is this thing up here? We can actually isolate this and think about this in the following way. I just told you what happens if I transform the data by projecting it onto an axis. And I told you how we get the mean and the variance of the stuff that lands on that axis. What if the axis is just the horizontal axis? So we let v hat equal 0, 1. Okay? Sorry, 1, 0. So if I do that special case, I'm going to erase this now, because this is just the derivation that we had for the transformation. And now I'm going to write, if v hat is equal to 1, 0, then what is the variance of the stuff? We're projecting the data onto x-axis, right? That's what that means, because now v hat points in this direction, and we're just dropping all the data down onto the x-axis. And what happens when you drop the data onto the x-axis? You're just taking its horizontal component, right? That's what that means, right? If you multiply one of these data points by take a dot product with 1, 0, what do you get? You get 1 times the horizontal coordinate plus 0 times the vertical coordinate, so you get the horizontal coordinate. Fine. Now we take those things, and we take the variance of those, you get the variance of the horizontal coordinate. Where does that show up in this matrix? That's why we're going through this. Well, all I have to do is take this matrix, multiply it on the left by 1, 0, multiply it on the right by 1, 0. Notice that this one is transposed, and this one's vertical, this one's horizontal. And when I multiply this matrix by those, what happens? Well, multiplied by the first one, what happens? I get a vector out. It'll be 1 times sigma x squared, 0 times this thing. So I get sigma x squared. And then I multiply the next column by this, take another dot product, and I get the sigma xy. So the product of these two, this and this, is a vector. I guess it's a row vector. Row vector, which is sigma x squared and sigma xy. And now I take a dot product of that with the 1, 0 on the other side, and I get the sigma x squared. Okay, good. Everything actually makes perfect sense, right? If I ask, what happens if I project my data onto the x-axis? I'm just taking the horizontal component, and what I should get out is the variance of the horizontal component, and that's contained in this matrix right here. So this thing is just the variance of the horizontal component. It's sitting right here. What is this thing? Well, you would get that result if you multiplied through by 0, 1, the vertical axis, right? If I project all the data onto the vertical axis, I get out the vertical component, and I ask, where does that show up in this matrix? And the answer is it's right there. Okay, so this is the variance. This is all about trying to understand how to interpret covariance matrices. So this is the variance of x component, and this is the variance of the y component. Okay? And what's that? It's the covariance or the cross variance between the two components. And it's kind of weird because it's a little hard to think about. If we think about it linear algebraically, it's kind of coming from the dot product of the x and the y. Right? That's what it is. It's like this one comes from x dot producted with itself. So it's the sum of all the squares of the x components. That makes a lot of sense. That's a variance of the x's. I do the same thing for the y vector. I get the variance of the y's. This one is this funny thing that's like a mixture of the two. Right? It's the combination. So this is not the variance of anything. This is a variance of something. This is a variance of something. This is like some other thing. What does this tell us? What do we do with this? Well, we've got to figure out how to interpret that. And I want to go through a couple of things to interpret that. Does anybody want to say off the top of their head what they think that means? Has anybody been through any of this before? You probably have. Do you have a name for this thing? Do you have ideas about what this thing controls? Remember that back to our geometry picture, right? We have data. What is the covariance telling us? Well, it's on the slide, right? It tells us the shape of the data cloud. So what does this thing tell us about? So somehow there's 3 numbers in here, because this one's duplicated, so it looks like 4, but really it's 3. Okay, so I have 3 degrees of freedom. And if I want to describe the data cloud using all of these descriptors, I also have the mean. So I have 2 numbers there, and I have 3 numbers here, 5 numbers altogether. What does this tell me about the data? It tells me how spread out the data are horizontally, right? So that's good. That's a dispersion measure horizontally. This one tells me how spread out the data are vertically. So it must be that this last one, since the whole thing is able to capture the shape of the data, and the shape of the data, well, would include things that are clouds that are shaped like that, clouds that are shaped like circles, clouds that are vertical, right? All of these things, right? Different shapes. It must be that this is somehow telling me about the shape, independent of the fact that it has this variance, this width vertically and this width horizontally. So somehow I have a width horizontally, I have a height, vertical height, and this must be capturing something else that's like the shape, something about the shape. Does that sound right? Okay. So how do we figure out what it is? Well, we have a couple of different ways to do this. One is we can go back to regression. So let's do that. What if I compute?
You're regressing past 11 o'clock.
Yeah, but I got to finish this. I got to at least write this thing down, and then we can do the other stuff after the break. So let me just write this, okay? If I fit these data with a regression line, what happens? You guys remember what this looked like, right? I have my y's and my x's, and I try to minimize, right? I minimize this. This is my regression problem, written with vectors, right? I take the y vector minus beta times the x vector. I square that thing. If I wanted to write it in terms of this data, what would it be? Well, let's write down the solution first, and then we'll come back and rewrite this in terms of the data. What's the solution? I want to minimize this. What's the best beta? Anybody remember? Nobody remembers. What was beta hat that minimizes this? I should write argument. X transpose y minus or divided by x transpose x. Okay. That's starting to look good. Remember what these things are. In the covariance matrix, right? This is C. C is, this was x. I'm going to write it as x transpose x. It's actually the length of x squared divided by n. This is x transpose y divided by n. This is y transpose x divided by n, and this is y transpose y divided by n.
All assuming mean-centered.
Yes, assuming mean-centered. We already subtracted off the mean. So, the regression solution is take this guy, the sigma xy, and divide it by the other one, sigma x squared. Right? This thing divided by that. That's the optimal solution. So this, and remember that what is the regression solution? Beta is a slope, right? It's the slope of this line. So what I'm saying is the slope of this line, the best fitting line, is you can get it out of the covariance matrix by taking this entry and dividing it by that entry. That's beta. So the regression solution is embodied. It has to be embodied in here because the regression was a least squares problem, and this captures everything about basically the entire quadratic description of the data. That elliptical shape up there captures the shape of the data in terms of its quadratic expression, right? In terms of its variance. And this thing gives you all the information you need about that, and you can read out the bits that you want. If I want to know how wide is the data, it's this. How tall is the data, it's this. And the slope of the best fitting line in a regression sense is this divided by this. It's a little bit funny, but it's there. What about, but the thing that's worth noticing here, and then we'll be done, is that this expression, y minus beta x, is just d times a column vector that looks like minus beta and 1 transposed. So if I took a vector minus beta 1 and multiplied it by d, what I would get is minus beta times that x vector plus 1 times that y vector. And if I computed the length of that, the squared length of that, that would be this regression problem. So the regression problem is really just saying, if I stick in this vector and take my data and smash it onto the thing defined by this vector and measure the variance of that, which we know how to do, what's the data that minimizes that? So we can sort of see this problem as described in terms of just a transformation of the data, transforming by projecting it onto this line. It's not quite a projection because this is not a unit vector. Okay. We'll stop for a brief break, and then I'll finish this, and then we have lots of other stuff to do. Okay. Regression. So here's the solution to the regression problem, written in this kind of new format. Okay? Sigma xy divided by sigma x squared. If we this thing, as I already explained, can be written as the vector minus beta 1 times the data matrix, assuming the mean is already subtracted out. Okay, so what I want to do is write that thing, minus beta hat, comma 1, that's a vector, times d, and I want to compute the variance of this thing. But we already know how to compute the variance of any linear transform of the data. This is just yet another linear transform of the data. This thing is basically a matrix that has only one row, and it's got these two elements in it. So I go through and I calculate what the variance, and the answer is, I take the original covariance and I sandwich it between this vector and its transpose. Okay, so here's minus beta hat 1 on the left side, transposed, times c times minus beta hat 1. And I was going to write this out, but I feel like I'm filling the board with too many bits of math that are kind of annoying. So I'm going to sort of just jump to the answer. You can work this through yourself, because this is just matrix multiplication. If you multiply all of this out, vector times matrix times vector, and you collect all the terms and cancel things out, you end up with something that says that the variance of this thing, that is the value of this expression, is sigma y squared minus sigma x squared over sigma xy squared over sigma x squared. Okay? So it's this thing minus this thing. So how do we interpret this? This thing is saying, if I take all the data and I calculate this, I take every y coordinate and I subtract from it beta times the x coordinate. What am I doing? I'm taking every point and I'm taking its x coordinate, I'm multiplying it by beta. Well, beta is the slope of this line. So if I multiply the x coordinate of this point by beta, what I get is this height, right? Multiplied by the slope, and I get the height. It's basically, I get the value of this line at that location. And what I'm doing when I subtract them is I'm taking the difference between these two things, this height, and then I'm squaring it. And if I do that for all the data, all I'm doing is I'm asking, well, how far is each data point from the line? And take the sum of the squares of all those distances, right? That's how we define the regression problem. Measuring the distances, it's what's on the slide, right? Measure the distances of all the points of the line, square those distances and add them up. Okay, so this thing, what I'm computing here, is the average of those distances, because it's not just adding them up, I'm dividing by n. Okay, so this thing, the variance of this is equal to this, and what is all of this? So I have the variance of the data around the line, or after the line has been kind of subtracted out, and that's equal to sigma y squared. What was sigma y squared? That's the variance, that's the original variance of the data, at least in the y direction. So if I were to splat all the data onto this axis, and it ends up showing up, and if I make a histogram and it looks like this thing has a mean, which is 0, I'm assuming, and it has a width, which is sigma y. Sigma y squared would be the variance. Okay, so they have the original variance of the data vertically, minus this thing. So I have the variance around the line is equal to the original data variance minus this thing. So we can think of this as the original variance, and this is the amount that is explained by or captured by the line. And this is the residual variance. So the equation, the way to read this equation is on the left side we have the residual variance, the variance around the line, and that's equal to the original variance, the total variance of the data, minus the part that we explained with the line. We're writing it the other way around. The total variance is equal to a sum of two variances, the variance around the line and the variance that's been captured by the line. Okay. So we've just done another one of these partitions of variance. When we went through this thing of subtracting off the mean, and I said actually you can represent the covariance as the second moment minus the mean, the squared mean, I was kind of saying that you can partition the total sum of squares, that's the second moment, into two pieces. There's the variance, that's the bit around the mean, and then there's the mean itself, the squared mean itself. This is very similar in nature. What we're saying is the variance, the total variance of all these points can be captured in two parts. One part is the part that's explained by the line, and the other part is what's left, the residual. Okay? All right, so we have three pieces, and they correspond to this, and they can be read out from this covariance matrix, right? So sigma y squared is here, sigma xy is here, sigma x squared is here. So if I take this one minus this one squared divided by that one, I get the variance that's explained by the regression. Or the variance that's residual after I've subtracted out the part that's explained by the regression one. We have actually a linear algebra way of thinking of all of this. So this is, I remember when the first time I learned about this, I found it really confusing. I kept trying to think through all these, it was all written out with summations, and I kept writing all these equations and trying to figure out what does this have to do with anything. But you have actually simple geometry to explain all of this, and it goes like this. This is a different space. What we're going to do is we're going to think of x, the vector x, that lives in an n-dimensional space. That's not this space where the data lie. That's the complementary space where we take the horizontal coordinates of all the data points and string them out in a big n-length vector. That's this vector. I can only draw it, unfortunately, in 2 dimensions. But it's n-dimensional, right? And then there's another vector, y. That's all the y coordinates, okay? So what are we actually doing when we do all these calculations? Well, we already wrote it out in terms of these vectors, and it's written here. I left these on the board on purpose, because this is the way we usually think of covariance. We write these variances of the x and y coordinates, and then there's this cross term, the covariance term. But we can also think about it this way in terms of these vectors. So this is just x transpose times x, or if you like, the squared length of x divided by n. This is x transpose times y. And what's actually going on here, let's think about the following. We talked about the regression problem when we first set it up as what we want to do is find the point along that vector x that can explain the data best. And the way we thought about that is we said, well, gee, if I extend any multiple of x, i.e. beta times x, it's just going to be something along on this line. And all I'm really trying to do is to find the point on the line that's closest to y. And the answer to that is geometrically very easy to see. It's and we drew this at the time. We said you draw the perpendicular from y onto this line, and this is what we're looking for, that point right there. And that is going to be our best explanation of y using x. That's what regression is about. We turned the regression problem that looks like this thing with the scattered data points into this more abstract high-dimensional problem, and we said, but the reason to go into that space, that high-dimensional space, is then it's very easy to see what the answer is. And in fact, it's easy to do this calculation. And how do we do that calculation? Well, you kind of take x. What you want to do is think about projecting y onto this line. So how do I do that? I take y. I take its dot product with, well, I need to make it a unit vector if I wanted it to be a projection. So I write x, but I divide x by its own length. Right, so I make x into a unit vector. I take y, dot it with x. That gives me this projection. That's the distance that I need to go. And now I take that number and I multiply it. So what's that? I take that number and I multiply it by the unit vector x. So I multiply it by x over its length, like that. And that's this is beta times x, or beta hat times x. It's the best we can possibly do, right? And if I think then about the total length of y, what is the length of y? It's y transpose times y. That's sigma y squared, except for the divide by n. So this is the length of the y vector, effectively. What's this? Before I wrote out the solution, let me back off one and ask you, what's the length of this vector from the origin to here? It's just this, right? It's the length of that. Y transpose times x made into a unit vector is the projection. It's the length of this piece, right? So what is the length of this piece? Well, let's write it out. This is just y transpose x over the length of x. And if I wanted the squared length of that piece, it would be y transpose x squared divided by the length of x squared. And that is just sigma xy, this thing in the numerator. And this thing in the denominator is sigma x squared, but the square root of that, so it's just sigma x. So really, this thing is sigma xy divided by sigma x. I left out the divide by n's, but it doesn't matter because they're both divided by n, so those don't make any difference. This is that divided by n, this is that divided by n, the n's go away. Okay? So now we can start to interpret this equation in terms of this geometry. The squared length of y, we can think of that as, I'm going to just write sigma y squared, and you're going to remember that I've ignored the divide by n here. The length of this thing is sigma y squared. The length of, here's x. The length of this thing down here is sigma xy over sigma x squared. That's this thing. And this is the residual. The red thing is what's left. It's the part of y that we can't explain, right? So we can explain a large portion of y by adjusting x to have this length, and that's the most we can explain, and then this is what's left. So this expression about partitioning variance into the total variance of the data and the part that we can explain and the residual, so this is residual on the left is equal to the total variance minus the part that we can explain. It's just the Pythagorean theorem. It's the Pythagorean theorem. It says the total variance, that's the length of this guy, is just the sum of the squared length of this guy, is the squared length of this guy plus the squared length of this guy. That's all it is. It's just rewriting the variances, this variance as a sum of these two pieces. And this equation is exactly the same thing. Okay? All right. One other little observation here, while we're at it with the geometry. You remember, I hope, erase this thing because it's in my way. You remember, I hope, that there's, if I define this angle as theta, the angle between x and y, I can write this y transpose x as the length of y times the length of x times the cosine of that angle, right? This is a dot product. So this is going to be sigma, the length of x, that's sigma x. The length of y, that's sigma y. And then there's the cosine of theta. And of course, I still have in the denominator sigma x. The sigma x's cancel. This is sigma y times cosine of theta. So I can think about this, the length of this thing, this is the explained variance, right, as being the original variance times this cosine, which is the angle between these two guys. Right? And if I wanted to know, instead of just expressing the angle between these guys, instead of just expressing it this way, the actual variance, if I wanted to know the proportion of variance that I've explained, so I've explained that amount of the variance, and there's another part that I haven't explained. If I want to know, well, what fraction did I explain? Did I explain all of it? Did I explain 90% of it? Did I explain 20% of it? 30% of it? More of it is good, right? And you can see from the picture the way this works, right? If theta is 0, then I've explained all of it, right? Cosine of theta is 1, if theta is 0. And I've explained all of it because I can actually make x reach y. If this angle is 0, that means x is pointing in the same direction as y. If x is perpendicular to y, then I can't explain anything. And then, because the cosine of the angle is now 90 degrees, and the cosine of the angle is 0, so the amount of explained variance is 0. What I might want to know is not the absolute variance, but the fraction. So if I want the fraction of explained variance, so fraction of explained variance is what? Well, it's this. This is the explained variance. Sigma x squared, sigma xy squared over sigma x squared, divided by the original variance, which is sigma y squared. Right? And what is that? Well, sigma xy, we just wrote it, is sigma x times sigma y times the cosine of theta. Sigma x, sigma y, cos theta, and we're squaring it. And then we divide that by sigma x squared, and we divide it by sigma y squared, and this whole thing is just cosine squared of theta. Okay, there's a name for that thing. Let me write it out. This sigma xy divided by sigma x times sigma y, that thing squared. Anybody know what that is? The fraction of variance explained. What proportion of the variance do we explain by using x to describe y? There's a name for that.
R squared.
R squared, right. So and when you read about this, people usually use the letter R to describe this. They say R squared. This is the proportion of variance explained. And R squared is just, if we want to think geometry and dot products and things, R squared is just the squared cosine of the angle between these two vectors. So now we see R squared is a number between -1 and 1. When it's 1, it means we've perfectly explained the data. That means x and y are pointing in the same direction. The cosine of the angle is 0. When it's a little less than 1, we're explaining it reasonably well. When it's a lot less than 1, when it goes towards 0, we're not explaining it at all. And if we go in the opposite direction, it starts to be that we're kind of flipped suddenly, and we're anti-explaining it. That's not going to happen in these cases, because what'll happen is if x is pointing in the wrong direction, you'll just get a beta that's negative. So you really won't need to worry about things in terms of regression, in terms of explaining negative amounts of variance. But it can happen in general that you need a negative beta in order to capture the variance. Okay. So we now have, so this thing r squared, and the square root of that is called r. It's called the correlation coefficient, or Pearson's correlation coefficient, or full expression. And it just captures basically how related the two variables are. That is, if you did regression, how much of the variance could you explain and why? What proportion of the variance could you explain and why, given the knowledge of x? Okay. So all of this is sort of connecting a little bit of linear algebra that we've done that has to do with these x and y variables, back with covariance matrices and the description of that quadratic form and the ellipse that I had in the previous slide. All right, so I think that's all I want to say about that, and now we have to kind of dig into a few other things in the remaining 10, 15 minutes. Okay. There's a picture of the correlations that you get for these different data examples. So when x perfectly explains y, the correlation is 1. Because basically, if you subtract off the part that's explained by x, there's nothing left. Or if you want to say in terms of this picture, the x and the y are basically pointing in the same direction. And here it is, the correlation coefficient of 0.8. So here you subtract off the part that x explains, and there's still some residual variance. It's the amount of variance, this is r, so if you square it, the amount of variance you've explained is 0.8 squared, and the residual would be 0.2 with 1 minus that, okay? Et cetera, et cetera. Okay, I'm going to skip past so that we can get started on the next chunk. I have a feeling that I'm not sure which pretty pictures you're thinking of.
Those are correlations that make no sense. The dinosaur or whatever.
Oh, yeah, no. I'm going to wait. We'll wait because it's later. Too soon. Okay. So now, all of that was basically to try to bridge a little bit between descriptive statistics, which we've been talking about, and a bunch of the linear algebra that we've done previously. We're going to be able to do lots of calculations in statistics using linear algebra. And so that little chunk of stuff was just to remind you that you know how to do these sort of vector and matrix manipulations that allow you to calculate things like means and variances, or means and covariances. They allow you to project things into spaces. They allow you to measure combinations of things in these ways. And they're actually all related to standard statistical descriptions that people use, meaning covariance and correlation. Okay. We're now going to step away from descriptive statistics briefly and sort of say that, the way this actually works is that rather than just talking about calculating these things on the data, what we're going to do is we're going to start thinking about trying to infer things about the data. So how do we get to that? So let's start here. Let's say I have a bunch of data points, xn. I showed you a histogram like this before. This is not really even a histogram. These are just where the data fell. It just happened that I measured this one twice. So here's a bunch of data points lying on a seesaw. And we looked at this when we talked about descriptive statistics. We talked about measuring the central tendency and the dispersion of that. Okay? Now we have an idea that all of you have seen many, many times, starting at least in middle school, if not earlier, which is the idea of a histogram. When we measure data, we often summarize it not just with mean and variance, but if we have a lot of data, often we'll try to summarize the shape of the distribution by computing a histogram. So what's a histogram? You basically take the data and you bin it. So you decide on a bin size, and a general form of histogram doesn't have to use equal size bins, but normally that's what we do. So you pick bins of some width, that's what these bars are, and you count how many data points fell in each bin, and you draw a bar whose height is the number of data points that fell into that bin. And you notice when you do this that it does capture something about the data. There's a plus and a minus here. Okay? So we're trying to summarize data. And that's what we were doing with mean and variance. That's what we were doing with median and the mean absolute deviations. That's what we were doing with all of those measures of central tendency and dispersion. If we want a little more detail, we might do something like this, make a histogram. The histogram is still a summary. So I have 1, 2, 3, 4, 5, 6, 7, 8 data points here. I have 4 histogram bins here. The representation of the data is very different. So this is the raw data. This is just a set of x's that were measured. What is this? Well, to specify this histogram, what I have to do is tell you where each of the bars are. That's these C's. C stands for center. The center of each bin. And then I have to tell you the height of each bin, or the count that goes with each bin. And altogether, that describes the histogram. This is a summary of that. Once I've done this, I can't go back. Just like once I give you the mean and the variance, you can't go back to the original data. I haven't told you what the original data values are. I've summarized them, and I've done a dramatic summary when I give you the mean and the variance. Right? I'm giving you 2 numbers. Maybe you started out with 10,000, and I'm giving you 2. So the same thing here. If you started out with 10,000 data points, but you only have 10 histogram bins, I've gone from 10,000 numbers down to 20 numbers, I guess, because I have to specify the position of each bin and the height of each bin. If the bins are all the same width and they're side by side, maybe I don't even need that many numbers. I need 10 for the heights, and I need the first position, that's 1 number, and I need the width, or the spacing between the bins, so I need 2 numbers, so I need 12 altogether to capture 10,000 data points. But I've obviously lost something, right? What have I lost? I don't know where the data fell. I know how many data points fell in this bin, but I don't know where they are. Within this bin, it might be that they're all piled up on the left side, all piled up on the right side, all in the middle. I have no idea. Once I hand you this, you don't know within each bin where the data fell. You just know how many points fell in each bin, each bucket. Think of these as buckets that are collecting rain. And they fill up by different amounts because the rain is heavier. The rain is heavier here than it is, let's say, over here. So you've got bins collecting rain, and at the end you shut everything off and you say, well, how much did I fill each bucket? You don't know where the raindrops fell within the bucket. So you've lost some detail, but you do know how much each bucket obtained. Okay, so that's a histogram. If I want to do a calculation of the mean, how do I do it here? I add up all the x's, divide by n. If all you know is this, how do you compute the mean? You sort of can't. You can't actually get the true mean of the data, but you can calculate an approximate mean from the histogram. How do you do it? You make the very simple assumption that all the data points that fell in each bin actually are just sitting at the center of each bin. And then you just take a weighted sum of those. So you take this center, say I have 10 data points that fell here, I have 3 data points that fell here, or another 10 here, and then 3 here, 0 here, and 3 here. So I just take each of those numbers multiplied by the center of the bin and add it up. So what does that look like in terms of this? If this is this is a vector and this is a vector, the centers and the heights, right? These are both vectors. Right? In this picture, there's 1, 2, 3. Let's say there's 1 here also because it's empty, but it's there. So 1, 2, 3, 4, 5. There's 5 centers and 5 heights, so I have 2 5 vectors. How do I calculate the mean? It's a dot product. I just take a weighted sum of each center times the number of things that fell in that. Oh, and then I have to normalize it. So I have to divide by the total number of data points. So it's a weighted sum of the centers multiplied by the number of points that fell in each bin, and then divided by the total number of points. Right? So how does that look? Write it down. And I'm writing this to prepare you for writing all the other stuff that we're going to write. So I would just take C as a vector. I would take its dot product with H. And now I have to do, so C is the centers, and H is the counts, I guess, for the height of each bin. So I have to do, underneath this, I have to divide by H dotted with 1. Why? Because, yeah, I'm writing dot products, but that's fine. You're right. Technically, we should put transposes on these, and that's fine. These are dot products, right? I'm taking the weighted sum of all the centers, multiplied by the number of points that fell in each bin, and then I have to add up all the number of points in all of the bins. That's what this is doing. the sum of all the ages, all the elements of age. Okay? So that's how I compute the mean, or an estimate of the mean. All right. Now the frequentist view of probability is that if I keep collecting data, I'm going to get more and more data over here, and it becomes unwieldy to keep all of those measurements. If I have 10 million data points, I have to keep 10 million numbers. So what I can do is make a histogram, and I'm going to make the histogram smaller and smaller in terms of the width of the bins. As I get more and more data, I can make the bins smaller and smaller. And eventually, in the limit of infinite data, if these are real valued quantities that are coming in, the x's, they can have any value, I'm going to end up with some nice smooth curve that describes the distribution of the data points. And that's what we think of as a continuous probability distribution. When we write something like p of x here, which is the probability of x, it's the function that describes this thing. And this thing, this histogram, the sum of all of these bins was the total number of data points. If we normalize the histogram, we can divide by that total number. That's what we were doing here. And then the histogram would sum to 1, and we could think of each of these columns as the proportion of numbers that fell in each of those bins. And this thing has that property. So if you think of these as really, really tiny bins, it's a nice smooth curve because it's made up of little tiny bins, and they're so small you can't even see them. And we've just plotted basically the center point, C, and the height of each bin. And the points are so close together that they form this continuous curve. Okay? And the integral, the sum under here, becomes an integral once this becomes continuous. And the integration under here has to add to 1. Okay? So that's our definition of a probability distribution. All right, we're gonna now start working with probabilities, and we're going to be thinking of them. And let me just give you the framework for what we're going to be thinking about. So here's the original conception of description statistics. Doesn't worry about any of this. It just says, well, I've got data, and now I want to, describe the data. How do I? That's what the word descriptive means, right? I want to describe it. How do I describe it? Well, I want to capture something about where the data lie and how spread out it is, and maybe what shape it has. So that's what all of the things we were talking about are doing. Now we're going to do something a little bit weird, but this is basically how the field emerged. Right? The idea is that we're going to say, wait a second, I need some model, or I need to think about where the data came from. I'm not just going to say, I have these data and that's that, and I just want to describe them. In order to describe them, what I really want to do is I want to imagine that they came from some thing up in the sky, an urn. This is a Greek urn. If you're going to show an urn, it might as well be a Greek urn. And the data are actually drawn as measurements out of that urn. And the measurements that I made are measurements that depended on some state of the world. There's something that describes the thing I'm measuring from, so it's like I'm measuring the temperature of some liquid. I'm going to make a little bit of a switch into something abstract. I'm going to imagine that there's a true thing out in the world, let's say the true temperature, and these measurements that I'm getting are getting tossed over the barrier, and every time I make a measurement, it's a little bit corrupted. I'm not allowed to see the real thing. I only get these measurements that are kind of crummy versions of the real thing. And that's what I'm stuck with. Now, I can make a bunch of them, and I have this belief that if I make enough of them, eventually, I'm going to have a pretty good idea of what's in that urn. I'm going to know something about the distribution of things in that urn, and I'm going to know something about what the true temperature is, because that's the thing that is causing these measurements to look the way they do. So the entire endeavor now becomes an issue of, rather than just saying, well, here's the data, and how do I describe it, it becomes, no. What I really want is, I need a model. I need to fabricate some abstract model that describes where the data come from. And more specifically, I need a model that describes how the data, the measurements, are related to the thing that I care about. So there's something in the real world out there, theta, I'm listing theta as the thing in the real world. That could be like the actual temperature. And what I'm measuring are these kind of partial, crummy versions of that. And what I really want is to understand what's the relationship between my measurements and the real thing. And that'll tell me, well, how many measurements should I make? What kind of measurements should I make? How well have I captured the real thing? Am I close to it? Am I far from it? how should I design my experiment in the end? And so this becomes really an endeavor that's really underlies all of science. The idea that we have a model in mind of where the data are coming from, and then we use that model to do something that we call inference. So now that we've collected the data, we do something called inference, which is to kind of reason backward through the model and ask, well, what's actually there? Given that I measured these things, so the model is a description of where the data came from and how they're related to the thing that I want. The inference part is, I got to go the other way. Now I have the data, here's the measurements, that's what I got. What do I now know about the real thing? I'm not allowed to look beyond the curtain here. I have to stay on this. This is the real world over here. Over there is really just a model that I have, a description, a fabrication of what I think is actually going on. And so what I'm going to do is make my measurements, and then I'm going to try to, from those measurements, learn something about what's over there. And I'll see maybe in this process whether I've got a good description of what's over there or whether I've got a kind of mediocre description. I'll also, in this process, be thinking about what kind of measurements should I make, what kind of measurements can I make, how many measurements can I make a new device to make different kinds of measurements. And in that process, the goal is always going to be, I want to figure out something about, say, theta. That's what I'm trying to do. That's the inference part, is to figure out something about theta given the measurements that I have. Okay, so that's it. The reason this gets very, very complicated very quickly, because if this model is often not written down in a lot of literature, people don't even express what it is that they think they're measuring. They just go ahead and do things, and then it's not clear when they're making inferences. It's not clear what it is that they're inferring or whether those are justified. So a lot of the realm of statistics is to think about how to write these things down properly and how to think about what we can justify and what we can't justify. All right, so we're out of time, so I think we're going to have to stop. And I basically have failed to introduce basic probability. But Mike will do it in about 10 minutes. So it's classic for this course that, it's like an inchworm. It's like, I slow everything down, and then Mike zooms in. Slow everything down. Okay, see you next week.
Okay.